All right. Morning, everyone. We're all here. We're not all. Some amount of us are here. Those that are here are awake. So, welcome. Yes, it's cold. Good things, right? Quick logistics thing. This assignment's kind of existed. It's already been open. In fact, no one's done it yet. And that's fine. I haven't mentioned it yet, but I think it's been open. No, it hasn't been. Yes, it is. Whatever. It opened recently, January 26th. Due March. You got a long time to do this. So, just a quick thing. This assignment, using AI and effective problem solving. Look, AI is a thing. Everyone knows it's a thing, yada, yada. The reality is it's new to pretty much everyone. It's emerged very quickly. It's accelerated very quickly. A lot of people are using it now. But the reality is, like any new thing, people are all figuring it out. So to help you all with figuring out how to use it effectively, because it's one thing to use a tool, it's another thing to use it in a way that's effective for your desired goal. A lot of people currently kind of use AI to do the things for them. It does the work for them. And the problem is, if it's always doing everything for you, then what's the purpose of you as far as a job is concerned, or anything else is concerned? If it's doing all the work, then what are you doing? Like, what's someone going to pay you for? So to that end, one of the things I want to train you all in, and I'm not going to spend really too much time on this, is how to use it effectively for learning. Because, that's what you're going to be doing in the next few years, and honestly, this is one of the biggest use cases I've had for it. How do you use, what do we use the internet a lot of times for? Looking up information. This is kind of like the new internet in a lot of ways. It's more efficient. And the major theme with this, so I made a document based on my experiences of using it to assist with kind of solving physics problems. And more importantly, kind of the overarching idea with this. So this is not necessarily leaning on my vast experience with AI. I would not consider myself an expert in any means, but I would consider myself an expert in learning. Did my PhD in how to better in physics education research. I've been teaching for a bit. And my perspective towards AI, as far as learning is concerned, you want to approach it as if it's a tutor. You want to approach it the same way you would approach me, the same way you'd approach any of the tutoring services that are basically available. If you came to me with a problem and you said, hey, how do I solve this problem? I am not just going to go to the board and then solve the entire problem in front of you. In a lot of ways, that's how people use AI. And that's fine. There is value in just like, hey, give me some information. But I have kind of some analogies here, and I mentioned this a few times. It's effectively like saying, hey, I want to learn how to drive. And someone says, okay, stand here. I'm going to drive around for a bit. You can watch me drive, and then you'll know what to do. And we all know that that's not how any of that works. That's not how any learning kind of happens. So what I want to kind of get towards is level 3, where basically you are the one in the driver's seat, but it is kind of there with you. Maybe it has some lane assist, cruise control. It's kind of giving you some guidance here and there when you get stuck. It tells you when to brake before you hit something, stuff like that. These later ones are kind of more the creation route, so I'm not expecting you all to get all the way to the end where you're actually making problems, because honestly, to kind of use AI to its fullest, all of these levels are good. All of these levels are good for different things. Sometimes you just want information. Sometimes, I want to ask when was the last moon landing. I don't need it to ask me a bunch of questions to guide me there. It's just fact. I want the fact. I want you all to use level 3. At some point, you all do want to use AI for level 5, which is using it to co-create, to make things, and create things in a way that's beyond what you normally be able to do. So, coding is a big example of that. Using it alongside coding is incredibly useful. Don't have it do all it for you. Have it do it with you, whatever. That's kind of the end. So I currently use AI various times to make multiple different versions of problems. However, I don't just say, make multiple different versions of problems and then give me some answers, and then I copy and paste it and stick it to the thing and say, yep, those are totally good. It will be wrong a lot of times. It's not just, hey, do this and done. There's a lot of times I have to check it. I have to say, hey, I want you to edit it this way, fiddle it this way. It's a back and forth, back and forth, back and forth. And that's kind of true of most of these, the back and forth. So the major theme here, make it a conversation. If you don't remember anything, that's kind of the major guide here. Make it a conversation, not a one, give me the solution, I'm done with you. Make it a, hey, I have this problem. I've done these steps. What do I do next? Give me some guide, or help me understand what the next step might be and why. Or you can use something called guided inquiry, which is what I do when people come to me in my office hours. When people ask me, how do I solve this? I don't tell them how to solve it. I immediately ask them a question. First, I look over their work. I see where they're at. And then I say, okay, what are we solving for? I kind of walk through the process and all that kind of stuff. The fancy name for that process is guided inquiry. It's exactly what it sounds like, guided questions. You all can tell it to do that. Hey, I'm solving this problem. I want you to use guided inquiry to help me through this. And it will know what guided inquiry is because it's got access to the whole internet, and that jargon means something. Another thing you all can do is take a picture of your work and actually just like, hey, here's where I'm at. Ask me a question to help guide me to the next step. Don't tell me what to do. Guide me to what to do. It's really good, actually. So I can only speak of my one experience. I used the paid ChatGPT version of this just to test it. I solved the problem. I didn't even write most of the steps. I just said, hey, here's a picture of my work. Tell me what the problem is and what I was doing, just to see if it could read it. And it did an exceptional job. It basically identified it perfectly, what I was doing, why I was doing it. And it wasn't pretty. I hadn't it was just scratch work that I'd kind of done on the side real quick. So it does a really good job of that. Make sure that you give it information, because if you do not, AI currently is a people pleaser. It does not ask follow-up questions. If you do not give it enough information, it will just guess information. And it won't even tell you that it's guessed information. You will have to figure that out. It's just one of those things. It's like, you want an answer. So, look, I just assumed that you gave me everything you needed, and if not, I'm going to guess. You need to be clear with it. Check its assumptions, things like that, because it's going to do that. It's as if you had an assistant, and you said, hey, I want a coffee, and they come back and brought you a coffee, and you're like, this isn't what I want. This has 2 sugars and 1 cream in it. I like it black. You're like, well, I didn't know that. I just guessed what the average person would want and gave you that. It's effectively the same thing. If you don't give it enough information, it's going to just guess without asking for any clarification. So be specific. Again, follow-up questions are really important. Why did you do this? Could I do it this other way? All that kind of stuff. Anything you would ask another human, you can do here, and I recommend doing here. And last, here's a really important one. Don't give it the right answer. So I give you all the problem sets the right answer. Do not give it the right answer. Why? Have it get the answer, and if its answer is different than the one I put, it did something wrong. One of the things is, how do you catch when it's making a mistake? I give you the right answers. If you tell it the right answer, it might fudge some things to get there, as people sometimes do. Don't do that. Don't give it that information. Use that to let it kind of make sure you explicitly ask it to solve it out in the background. You might even say, hey, when you're working through this, don't show me the answer, but I need you to actually solve it out. I have had it do many times. For example, I said make multiple versions of a problem, and it spits out 4 answers. And it says this is the right answer, and it's not right at all, because it actually did 0. I don't even know what it did. It didn't do any math. It just somehow got an answer from who knows where. Other times, I have had it solve it, and it's gone through all the algebra. It showed me the equations. It's looking good. The final expression is perfect, and the final answer is wrong. And they had the right equation there. Everything was right. I just don't even know what happened. I don't know if they just didn't plug in the numbers, maybe. It's a weird thing that happens. It does make a lot of mistakes. And so this is where you can check that. And then, you can ask it to find videos, websites, resources, all that kind of stuff. This is a tool. If you do not learn how to use this effectively, you can still learn. But my current perspective on this is you'll be less efficient than everyone else. It's like when the internet came out. You didn't need the internet to learn the information. You could still go to the library and read a bunch of books, but it is less efficient. Not many people are going to libraries anymore to learn information, because the internet exists, and it's effectively a huge, huge, huge library that you can search really easily. AI kind of is another synthesis of information, another level of that. So all that to say, this little handout exists. This assignment is really easy. I'll show you what it looks like. It's automatically graded, so no matter what you put, use some large language model, another name for AI, to assist in solving a physics problem you're having challenges with. Now, I said physics. This could actually be any STEM problem. I don't really care if it's necessarily from this class. Any STEM problem. If you're taking statics or anything else like that, go for it. Probably not coding. You could kind of do coding, but coding deviates in some ways. It's very syntaxy. Any problem you want, put the prompt there. What prompt did you give? What was your first follow-up question, second follow-up question, and third follow-up question? Because that's the most important thing out of all this is make it a conversation.
I will say AI doesn't really like statics.
Yeah.
So be careful with that one.
Sure, that different fields.
I learned that one the hard way.
Yeah, and that's kind of interesting. And the last recommendation I give here is which large language models should you use? Whichever one is the non-free version. That's kind of a major rule of thumb. Any of the quote-unquote paid versions will be better than unpaid. I guess you can get, like, as a student, the Copilot one, the paid version for free right now. Fun fact, all the companies do this. They like to give free things to people while they're students. And you're like, oh, how sweet of them, how kind. Take advantage of it. But the reality is the reason they do that is once you graduate, then that's what you're comfortable with, and that's what you'll be willing to pay for once you have a job. So that's why they do this. Fusion 360, it's a CAD software. They have free education license. Why do they do that? So you get used to using their software so that when you get a job one day, you're like, the company's like, hey, what CAD software do you know how to use? Fusion 360. You're like, okay, we'll pay the $1,000 license so you can have that.
Fusion 360 also has a free personal
Yes,
version.
they do, which is, yeah. So anywho, take advantage of these things as a student though, but just know it's not, know behind the scenes that they are trying to like trap you into their subscription model. It's good to be aware of that. Take advantage of it though. It's free. Like, but yeah, nothing is free in this world. There's always kind of a thing behind it, as rough as that sounds. All right. So there you go. Make sure you get this done within a couple months. The reason I'm mentioning this now is we got our test in a couple weeks, and look, these things are super useful for learning. They're incredibly useful, incredibly powerful. And I want to support you all in it because it's something that's new and most people don't know how to use effectively. So here's me attempting to assist in any way I can. Okay. Jumping into physics stuff. Gauss's law. This is what we started with last time. I want to remind you all what's the point of this entire PowerPoint. Find electric field. This entire PowerPoint, Gauss's law, this whole process, the end goal, find the electric field. That's the purpose of this. If you don't know why you're using it, you're not going to get the answer right. Like you do remember, the most important thing is always, what am I solving for? So, let me make a quick summary, like main points here. Just kind of gets plopped in here. Main points. Gauss's law lets us find electric field due to charge distributions. 1D, 2D, and 3D by using symmetries. So symmetry, remember we looked at a bunch of ones and different symmetries, made it so we didn't have to do the integral. Reminder to you here is Gauss's law. I'm just going to copy and paste it so we can actually have that. There's Gauss's law in all its glory. All right. So there's Gauss's law. And then for 1D rod, and I'm just going to copy and paste this from the other slide as well. Going to copy this. Boom. This is what we kind of learned so far. Here are the three geometries. You kind of start with this left side. Solve for E.dA. We choose for a line of charge, we use a Gaussian surface. Gaussian surface, that's a cylinder through the thing. Gaussian surface, cylinder, around rod. There we go. It's fine. For a plane of charge, we did a Gaussian surface that was a cylinder through plane, and that turned that into that. And then for a sphere, we did a Gaussian surface, sphere. Yeah, it was a sphere. That's basically all there is to say there. The important thing is these Gaussian surfaces, those are those bubbles, have to go through the point that we're finding the field at. Remember the whole point of this, find the field. So we draw this Gaussian surface that goes through the place we want to find the field, point P, some random spot. And this is kind of majorly what we practiced kind of last time, which we spent most of the time on. Today we're going to do a couple more problems, really just 2, I think. And I'm going to teach you all how to find the charge enclosed when it's not obvious. So obvious means you have all of it or none of it. That's like super obvious when that's going to be the case. I say super obvious. It's should be. The case where we don't have all of it or none of it, that's the case that I need to kind of train you all on. There's a nice little trick to it. We're going to use density. It's going to be a grand time. For that, pick a random joke. I kind of did that before. All right. Why was it called the Dark Ages? Because it had so many nights. Like K-N-I-G-H.
Yeah.
But also darkness. Great. All right, so. Yeah. This is good for your health. Okay, so I'm going to actually steal this problem. So we did this problem last time. We did a silver rod. We said the electric field inside it was 0, so that was super easy. And then we did outside of it, and we derived that actually kind of before this. We then did a plane of charge, and the really interesting thing here with the plane of charge, the electric field did not depend on distance. The electric field did not depend on distance. The electric field did not depend on distance for an infinite plane of charge. I could be 1,000 miles away from this plane of charge, and I have the same electric field as if I was a millimeter away from it. Now, the key point here is it's an infinite plane of charge. And then the question is, do infinite planes of charge exist? The answer is, what is infinite? And the logic I'll give you all, and I mentioned this a few times, this wall is not infinite, but if I get really close, I can no longer see the edges of it. So as far as I'm concerned, it is. That's kind of the logic here. When you all go outside, obviously the earth is not infinite, but it seems to go on really far from your perspective. And so we can use that. These are called approximations. And they're very useful. Now, if there was a plane like this wall, my analogy was when I was in the middle of it, I couldn't see the edges, so it's effectively infinite. Yes, if I move my face close to the edges, it no longer looks infinite, and so our infinite solution doesn't quite work on the edges. We call those fringe effects. And that's, you have to do more rigorous calculations for those edges, which may or may not matter, depending on your application. There is a statement of good enough. Sometimes things, if it's 99.9% accurate, sometimes that's good enough. Sometimes 99.9% accurate isn't good enough. All depends on your use case. So, plane of charge. All right, we're going to do this rod of charge again. And this is kind of the simplest case I can do with you all. We're going to do this rod of charge, but we're going to make an insulator. So same exact problem, but I'm going to change one thing. An insulating rod of radius 3 centimeters has a charge density. We already did part A. That's the same. So I'm not going to redo part A. In fact, I'm just going to look, I'll leave it there because it's the same. I'm even going to leave the picture. I'm going to make my life so much easier. There's my beautiful picture from before. It's the same picture. Yay. Part B. Find the electric field at a point 2 centimeters from the center. The answer here is no longer trivial. Trivial usually just means 0. Says find the electric field at a point 2 centimeters from the center of the rod, an inside point. So we are finding the electric field inside this. This is an insulator. It is allowed to have an electric field inside it. It is allowed to have an electric field inside of it. And actually, I need to do something. Let me think this through. No, I think we're all right. We're good. And we still have our linear charge density that will work perfectly fine for us. Let me make sure that that is a true statement. Yeah, we're going to say it is. All right. So, here's the key. You need to draw a Gaussian surface. This is a skill that if you don't draw this Gaussian surface, you're not going to know what you're doing and why. This bubble. You need to draw a bubble that intersects the point that I care about. And you need to draw the right bubble. If you don't know, This is just one of those things, if you don't do it, you're not going to know why you're doing anything in this problem. So, reminder to you all, for a rod, we draw a cylinder. This cylinder is inside of this cylinder, and it intersects the point that I'm finding the field at. So this is not a real object. It's a fake little bubble that I'm drawing. It's the math trick, though, that we do to solve this. And if we don't draw this, it's going to be really hard to understand what's going on here. So great, Gaussian surface. Gauss's law, we're going to write that. Remember, we're solving for E. Always with these problems, solving for E, solving for E, solving for E. We're going to use this equation, E dot dA equals Q enclosed over epsilon naught. Same old, Gauss's law. We always start there. The left side, we look at it and we say, oh, it's a cylinder. We use the rod. We use the sides of the cylinder. Same exact logic that we used before. So the left side is going to turn into E times 2 pi. And this is very important that you're careful here. We have two different R's. We have a capital R. That is the radius of the object, the actual physical rod. Let me make that a little bit, it's kind of got overwhelmed by my bubble. Capital R here is the radius of my rod, the physical rod. That's 3e to the minus 2 meters. That's capital R. We use capital R for like a set radius of a sphere, radius of a cylinder, like it's a set thing. It doesn't change. Capital R kind of, sets that in place. We use little r for some variable that's kind of like, that we've made up, that we've decided on. So in this case, little r is the distance to the point that I want to find the field at. This is not 1, in the problem it says I want to find it 2 centimeters away. So there's little r. Little r, capital R, not the same value. Two different measurements. Big R is the red line. Little r is the green line. I tend to usually make these dotted, but for the sake of making it easier to see, I kind of highlighted it more. All right, so this is where I was like, if you don't draw the picture, if you don't do that, this left side is the bubble. This left side is the bubble. It's not the area of the physical rod. It's the area of the bubble. What's the area of the bubble? It's going to be 2 pi times little r times L. Because it's the bubble. That's how Gauss's law works. Bubble. We're integrating over the bubble, the Gaussian surface. Left side done. It's the same equation we've honestly been using. Same one we derived before. Q enclosed. Q enclosed here. And this is where I might have to modify the problem. This is where making things up the spot can sometimes get me in trouble. Q enclosed is the charge inside of my bubble. The charge inside of my bubble. And I think this might work. We're going to see. I don't want to get things too complicated here, so I might switch what this variable is. Okay, here's the key. Q enclosed. I do not have all of it. I do not have none of it. I have some of it. Somewhere in between. I have some of the area, or some of the charge. Now again, this is where I'm going to go ahead and change this just to make it easier to explain. I could probably do it with this, but it's just going to result in more complications. So I'm going to make this easier. I'm going to change this problem. I'm going to say it has a charge density of -5 microcoulomb per centimeter cubed. In fact, let me make it even easier. I don't want to convert the units as much. This is now a volume charge density. I did this to make our life easier. You'll see what I mean in a second. I probably could have left it as linear, but this is ironically easier. Okay. Here's the thought process. Here's the logic. What is charge density? What's the equation for it? So charge density equals, and there's an equation for it. I'll give you all like 20, 30 seconds to think about it, see if you remember. We're going to use it. Definition of charge density. Volume. Charge density. All right, what do y'all think? What's the definition of regular density, mass density? Mass over volume. So what's the definition of charge density? Charge over volume. This is the definition, and this is a uniform charge density, meaning it's spread out everywhere the same. Why is this useful? How are we going to use this? If I know the total charge, which in this case I don't, but it's fine, we can figure it out, over the total volume, so actually, yeah, I want to teach this to you all in a certain way, so I'm going to say it has a charge. I know, I keep changing things. My apologies, but I want to train you on a certain way, and I keep realizing the way I gave it to you is not in that way. There you go. Okay. Insulating rod of radius 3 centimeters has a charge of -5. Now it's just a charge. It's just going to make it easier to teach you the way I want to teach you. All right, so this statement is true. If I know the total charge and I divide it by the total volume, that gives me the charge density. That's like the definition of how you calculate density. Charge over volume. Awesome. All right, this eraser is made of foam. If I wanted to find its density, so for those online you can't see, but it's just an eraser, you know, one of those foam erasers. If I wanted to find this thing's density, what would I do? Not a trick question. Take its mass and divide it by its volume, right? That's what the equation says. My question to you, if I broke this thing in half and only had half of it, how would its density compare to the whole object? Be the same. The density of a piece of this is the same as the density of the whole thing. That's the benefit of density. If it's uniform, even if I took a tiny, tiny piece of this off of it, its density is the same as this density. How would I find the density of the tiny, tiny, tiny little piece of it? It's the same process. What did you all do the first time? You took its mass, and then you divide it by its volume, and you get the exact same value. So my challenge to you all here, if the total object this works, here's the part, the important piece here. This bubble, we can do the same thing. Instead of saying Q total, we can say Q enclosed. And instead of saying volume total, we can say volume enclosed. Just like this eraser. I could take the total mass and divide it by the total volume and get the density. I could also take a small piece of it and divide its mass by its volume and get the density. So this is a true expression. Q total over V total equals Q enclosed over V enclosed, because they both calculate the same value, therefore they're equal to each other. This is the magic trick here. This is the secret sauce to solving this problem. To get Q enclosed, we're going to use that expression. Q total over V total equals Q enclosed over V enclosed. And we know everything in this expression, except for Q. We can solve for Q enclosed. So Q enclosed is going to equal Q total times V enclosed over V total. It's a ratio of volumes. It's basically, it's a fraction. How much volume do I have? Multiply that by the total charge, and that tells me how much charge I have. Now the question is, what is my V enclosed? It's a cylinder. It's just the volume of a cylinder. What's the V total? It's a cylinder. It's just the volume of a cylinder. So down here, if you want the V enclosed, it's a cylinder. So that's going to be pi. This is enclosed, the small bubble. So you have to be careful with your R's here. This is the mistake you might make. You need to know what you're doing. I'm finding the volume of my little black bubble here. What's the volume of that black bubble? It is pi little r squared times L. That's the area of a cylinder with radius little r. What's the volume of the big cylinder? Pi times big R squared times L. Same exact equation, different R. Times Q total. Pi cancel, L's cancel. Doesn't matter, that's an infinite rod. All we get is it's a ratio of little r squared over big R squared times the total charge. So then we're going to take that and put it over here, and that effectively sets up our problem so we can actually solve it. So therefore this equals little r squared over big R squared times Q total, all over epsilon naught. Epsilon naught still exists. All we did, and I'll highlight this for you all we did is took this expression and replaced Q enclosed with it. We found the amount of charge that was enclosed. It wasn't all of it. It wasn't none of it. It was some of it. How much of it? What fraction of it? We had to do that ratio. And that's the trick to doing these problems. That's the trick when you don't have all of it or none of it. And then, you rearrange this equation. One of these R's is going to cancel. We do run into a little bit of a problem where we have an L in the equation now. This is what I get for making up a problem on the fly. It's an infinite rod. It's going to have a bit of a problem, but we'll just ignore that for now. The thing that I care about, that's at least still useful. So you get R over 2 pi L R squared epsilon naught times Q total. Now, the way that this L would disappear is if I gave you all like a charge density instead. So this is where I could have given you all charge density instead of this. I could have said, had the charge density of this divided, 5 microcoulombs over 5 meters. Then Q total would have turned into lambda times L, and the L's would have canceled. So if I'd given you charge density, it would have canceled, but this just made my life a little easier to explain some things. So there we go. Cool. So this is what I care about is teaching you all how to get this charge density. How to get this charge enclosed when you don't have all of it, when you don't have none of it. And now we're going to jump to a much more complicated problem. Yeah. Yeah, if you wanted the value of it, you would plug in little r and big R. This is technically not solvable right now because it's an infinitely long rod. You know what? If I want to, and it has to be infinitely long for Gauss. Well, you know what? The rod is 100 meters long. Now we can solve it. And you might be like, but this isn't infinitely long. 2 centimeters from the center relative to 100 meters long it's relatively infinite long. We can pretend like it is. So that's the key here. And your answer will be, 99.9% accurate. Maybe more decimal places than that. I don't know. I'd have to do the real math. Okay. So let me show you all that summary slide just to show you that this is all here. Draw a picture with the right Gaussian shape. Did that. Solve for E.dA. Talked about that last class. What did we just talk about? Solve for Q enclosed. If the charge is completely enclosed, put that. If you have all of it, then you have all of it. Easy. If you have some of it, then we do this process here. Find the charge density. So for example, if it's rho, then you can do Q total over V total, and then you can say that equals Q enclosed over V enclosed. That's what that's saying mathematically. This is what we did. Set the two sides equal, solve for E, and don't forget the last bullet point. If you're inside a conductor, don't do any of this. Just call E equals 0. Don't forget that if you're in a conductor, that is just a true statement. And that's a very easy thing to put on a test, a multiple choice problem where I make it look like a Gauss's law problem, but then I say it's a metal. If it's a metal, I'll underline that it's a metal. I tend to underline things just to make sure that you're not skipping past it. And then it's up to you to realize what that might mean. In this case, if you're inside, it's 0. If you're outside a metal, it is not 0. So don't fall into that trap. Okay. We're going to do one more problem. That's all we really have time for today. And then next class, we'll start with voltage, electric potential. You are going to have a lab this week. You already had kind of a lab where you were using multimeters last week to measure it. This week, you're going to have another lab where you're actually going to see voltage as like a hill. And that's going to actually be very useful for as we talk about it. And I use the exact same analogy. I'm the one that made the lab. So, of course, they're going to line up with my material. But, the benefits there. Anyway. All right, so let's go ahead and we're not going to do this one. This is the one we're going to do right here. The answer looks terrible, but don't worry about that. You know what? Delete it. It's gone. All right. A sphere of charge. And look, these Gauss law problems, there's no shortcut, y'all. You just have to do them. Like every problem I'm teaching you all, if you're like, man, this is a lot of steps, seems so complicated, just try them. Just try them. Try the ones, if you're like really stumped, try the ones I taught you first, so you have the reference. But you need to be practicing these. This is notoriously one of the areas that last year on the test that people did the worst on. So that's why I'm like really stressing that practice this, practice this, practice this. There is no shortcuts. All right. Here we go. It's not as bad as it seems. It's not as bad as it seems. The answer made it look way worse than it was. The steps that we're going to do are exactly the same.
Little orange circles.
It's fine. All right. A total charge distributed through a spherical shell. A hollow spherical shell. So the inside's hollow. It has an inner radius of R1 and an outer radius of R2. Great. We're going to assume it's an insulator. I didn't specify that. If it doesn't say otherwise, assume an insulator. Basically, I'll tell you if it's a metal. Otherwise, on a test, I'll be more clear one way or the other. Let me actually put that. Through a spherical insulating shell. Let me practice good things. Insulating shell of inner outer radius. All right, we're going to solve for three things. The electric field, when you're inside R1, when you're between R1 and R2, and when you're outside of R2. Basically the three zones that we could possibly have. I didn't give you any numbers here. It's all variables, which is better because then we don't need a calculator. All right. Step 1. We're going to look at A. We're solving for E. Always remember what you're solving for. We're doing that in all these. Find the electric field. Find the electric field. Find the electric field. Okay. A distance R when I'm inside it. Where is that? Pick literally anywhere as long as you're inside it. I could pick this dot or this dot or this dot or this dot or this dot. It does not matter. Pick one. Pick any spot as long as you're inside it. You're going to get the exact same answer. As long as we're inside it, the solution that we're going to generate is true anywhere inside it. That's the benefit of working in variables. And we're then going to draw a nice little dotted thing and call this R. Oh, yeah, so inside here means less than R1. Less than R1. So, first step done. Whenever you all realize this is a Gauss's law problem, how do you know that? There's no other way to solve it. We're solving for electric field. You're not going to use Coulomb's law. Boom, you're in Gauss's law. That's kind of like your only two options are Coulomb's law or Gauss's law when it comes to these things. Draw the Gaussian surface. I'm going to give you all about 10, 20 seconds. Try it. Try to draw the Gaussian surface here. Pick the right one and then practice your drawing skills. It's a good question. Yeah. It's a good question. We're going to leave it at that. We're going to leave it at that. Yeah, that's a very important question. Okay. It's a sphere. We look at our list. What's a Gaussian shape? What's the bubble that we draw? A sphere. Now, you can get fancy and make it sphere. Oftentimes, to be honest, I just draw it as a little thing. As long as you know it's a sphere, great. Okay. Gauss's law. We always start the same way. Gauss's law says we should write this expression, E dot dA equals Q enclosed over epsilon naught. And then we solve for both sides. The left side, we're going to do E times the area of our Gaussian surface. It's a sphere. A sphere with radius lowercase r. The area of a sphere is 4/3 pi r cubed. That's the surface area of a sphere. It is what it is. It's just an equation. You all will probably derive that in Calc 3. Oh, actually terrible. I did bad. Catch the mistake. That's a volume. Volume's not area. How did I catch that? R cubed is volume. It's one too many powers. So I realized that after the fact. I was like, that's one too many R's. All right. This is a good memory test. What's the area of a sphere? It's going to have an R squared, and then what's in front of it? There's a pi, and then there's something else. It's a 4. These are things you need to know. They're not on the formula sheet. Warning now. Sphere, you all should know about spheres. They're like the most useful objects. Spheres, rectangular prisms, all that good stuff. Something you all should just know. All right, great. That's the left side. Right side. How much charge is inside that black bubble? Where is my charge in this picture? Is there anything inside of this? It's hollow. So how much charge is inside of that black sphere? 0. There's no charge inside that black bubble I drew. Because where's all my charge located? You know, you can make it positive or negative. Let's make it positive. It's all out here. It's all out. It's all there. How much is in the black bubble? None of it. So we did all this work just to say that E is 0 inside. This is the benefit of Gauss's law. Doing this with Coulomb's law? Awful. Awful, 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 awful. And this is true everywhere inside this. I picked a random spot. If it's true for a random spot, it's not like I just got lucky. That's going to be true everywhere inside that thing. No matter what bubble you draw inside that thing, you're not going to get any charge. Charge encloses 0. E is 0. Awesome. That's pretty useful. That might not have been very intuitive when solving this problem to begin with. You might not have looked at this and said, oh, that's the answer. Maybe you did, maybe you didn't. All right. First one done. Trivial solution. Part B. Still finding the electric field. Now we're going to draw a new one, and I'm actually going to do this on the next picture, on the next slide, because I need room. E equals 0. This one says find the electric, not 0, E equals question mark. Find the electric field at some point in between the two. Again, you can pick anywhere, here, 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 here. It doesn't matter. You get the same answer. So we're just going to pick some random spot. Boom. We are then going to draw our Gaussian surface. It's yet again a bubble. It's a sphere. Do the exact same process. Integral of E dot dA equals Q enclosed over epsilon naught. The left side, which is the integral, is ironically always the easy side. That side's always going to be the easiest. It's just E. It's the exact same thing. 4 pi r squared. It's still a sphere, a Gaussian surface of a sphere. If it's a sphere, that's what it is. Like that's going to be true at part A, B, and C. If you have a sphere, it's always going to be true. That's always going to be the statement. The right side is pretty much where the challenge comes in doing Gauss's law. The left side is, can you draw the right shape? If so, easy. Done. Right side, can you find the charge enclosed? And this is where I'll challenge you all. We know the total charge. We know this entire object is a charge of Q. The problem here is I don't have all of it. How much do I have? I can kind of color it in. Some of it. I have some of it. How much do I have? So we are, just to make this easier to see, we're going to have a radius r. So the radius r is going to be to where I'm finding the electric field. That's always good to kind of label on there. R1 and R2 are labeled. How are we going to do Q enclosed? The same way I taught you all. If you do not have all of it, and you do not have none of it, if you have some of it, Q total over V total equals Q enclosed over V enclosed. This is how you do it. This is that relationship. It's a uniform charge density. If it was non-uniform, I would go ahead and tell you you'd have to do an integral, but it would require like a double integral. I don't have the time to kind of go over all that. So you can do it for a non-uniform charge density, but you need integration to do so. So all yours are going to be uniform because they require double or triple integrals. All right. So rearrange this. This is actually bad. Rho equals that. I put Q enclosed does not equal that. That'd be nonsense. Rho equals that. That was the thing I told you all before. I miswrote it. We don't really care about rho, actually. We're going to solve for Q enclosed. So Q enclosed equals V enclosed over V total times Q total. It's the ratio of volumes. We got a couple minutes. You all try to build that expression. What is the volume enclosed? When I say enclosed, it's not the volume of the sphere. It is not the volume of the sphere. It is the volume of that black part I highlighted, of the physical object. The volume of the physical object. How much of the physical object is encapsulated by my bubble? How much of the, and then what is the volume of the total object? See if you all can figure out the volume of a cylindrical shell. It's really easy to derive. Really easy. All right. The key here is a hollow sphere is just a solid sphere with a sphere cut out of it. A sphere subtracted from it. A hollow sphere is a solid sphere with a sphere subtracted from it. So, if you all know the volume of a sphere, you can do this. Find the volume. So, let's look at V enclosed. What's V enclosed going to be? So we basically have a shell, just to draw V enclosed over here. We have a shell with outer radius R1 and inner radius R. That's that little black part that I highlighted for you all. That's the one that's enclosed by my bubble. So what's the volume of that? Okay. What is the volume of a sphere? I already gave this to you. I accidentally put it before. So see if you all remember. 4/3 pi r cubed. So we're going to make a solid sphere with radius R1, and then I need to subtract a sphere out of it. How do you make a hollow sphere? Solid sphere minus this. This is actually how CAD software works. You want to make a hole in something, you make the physical object, and then you make another object and subtract it out. That's how a lot of CAD software works. So this is kind of a good little thing. If you all want to, so we're going to subtract out the little sphere. And that's the equation for the volume of a hollow sphere. Big sphere minus small sphere. Do the same thing for the total. If I want the volume of the entire physical object, the big sphere now is 4/3 pi r2 cubed, because that's the big sphere, minus the little sphere, which is 4/3 pi r1 cubed. If you're like, what is he doing here? I'm finding the volume of this entire one, the blue, the entire object. All right. This looks gross, but a lot of things factor out. It's not bad. If you all hopefully notice, everything has a 4/3 pi in it. Wow, it's all gone. Yeah. Thank you. Yes. I drew my picture wrong here. Call me out when I do this. I made a mistake here. I made this black sphere. I made the black sphere have an outer radius of R1 and inner radius of R. That's backwards. Let me look at this picture here and show you the mistake I made. You're going to see me make these mistakes all the time because I'm a human. R should have been the outer radius, and R1 is going to be the inner radius. I mixed them up. It will happen to you too. Good news. If this is a problem on a test, it'd be a free response. If you mix those things up, you're going to miss 1 or 2 points. It's not going to really, out of 10. It's not going to really change much. You'll still get pretty much all the points. So R, let me fix these. Boom, that's going to be an R and an R1. So we're going to have R cubed minus R1 cubed over R2 cubed minus R1 cubed, all times Q total, which is just Q. Final step, put this up there. This is the charge enclosed, so put it there. So we get E times 4 pi R squared equals Q enclosed, so R, now I just got to write really quick so I can end in time. R2 cubed minus R1 cubed times Q over epsilon naught. Rearrange this so you get 1 over 4 pi R squared epsilon naught times R cubed minus R1 cubed all over R2 cubed minus R1 cubed. Yes, the expression looks crazy, but the steps to get there were not. The only challenge here is, do you know the volume of a cylindrical shell, in my opinion? That's like the only thing that made this more challenging than the other problems. Anywho, there's going to be this. I will post the test for you all sometime in the next few days to practice the test I used last semester. One of the free responses has a Gauss's law that's very good. I like it a lot, and a lot of people missed it. So that'll be a great one to practice too before you get to the R test.
Okay. Thank you.
Have a good one, y'all.